So what to expect in this video are these questions. So what exactly are embedding? So now it will come up with backend make out. What exactly are vectors? Like I am Ameer is that's how it works. This feeling, that's how it works. This feeling I want to give it to you. Hello everyone, welcome back to this channel, Accidental Data Engineer, and I am Ameer. And I've been teaching data engineering, data science, and GenAI on this channel for quite a long time now. It's been a year. And congratulations to each and every one of you because we just literally hit 3,000 subscribers. We are family of 3,000 now. We are family of 7,000 on LinkedIn, which deserves the moment of recognition. So thank you so much for that. So my next target is on this channel. I will teach you guys Gen AI, LLM, and everything about it, and how you can leverage these skills to be a modern data engineer. This is the part two of the series from data engineer to AI pioneer or AI data engineer. That's what I like to call it. So this is the part two. If you haven't seen the part one, go to the playlist. The link will be down in the description or in my channel. So go there, watch the part one. Also, I'd like to request you guys, if you are new here, subscribe to this channel and help me reach my goal, which is 30,000 subscribers before the end of 2025. So I believe in you guys. Let's do it. Okay, so let me just switch my screen real quick. Okay, so here we are from the data engineering to AI pioneer. So we are currently in the phase one with the foundations, and I'm assuming everyone who is watching this channel or this video will not have any background about LLMs, how do they work exactly, etc., etc., etc. So that's why this phase one, the foundations, is there. So today marks the lecture two, which is the start of the entire series. The lecture one was the introduction to what we are going to see and the common data engineering questions that everyone is asking me, how to be data engineer 2025. I have answered all of those common questions in lecture one, in video one, and now this is the lecture one where we are going to see what is an LLM and how the text to numbers work inside of the LLM. So I'm going to help you imagine how these LLMs work, or how LLMs see the world or see the human world, or do they really see how we see, or do they perceive it differently? That's what we're going to see in this video. And it really fascinates me, me after I built those visualizations for you guys, after I saw the visualizations, it was so clear in my mind that whatever I imagined it to be, I could show you guys now. And that's what I'm here for. Let's head straight to what it is and what it is not. Let's dive deep. Okay, so now that we have switched the screens to iPad, now let me walk you through the concepts of what LLMs are and how do they work. But before that, let me ask you this. Do you really think the LLMs see the world as we do, as humans we do, or they seem, or do they perceive the world differently? And that's the question that I have. So one of my roommates told me earlier that, and it's a really intriguing or interesting thought that I'd like to share with you guys, which is he said, "Mere universe is a mathematical equation that is a multivariable mathematical equation that humans really cannot visualize or perceive those number of variables in one single equation, and they cannot really solve that problem, or they are not able, or they are not there yet, so that the answer to that mathematical equation, or if you plot that mathematical equation, it will be the universe, how it works." And that's what these LLMs are about, if I would say. Basically, AI cannot read, or AI cannot understand the human texts, right? So you've seen these LLMs, you've been hearing a lot about Gemini, OpenAI's GPT, Google's Gemini, and then maybe Claude's Anthropic, all of these models, right? All of these LLMs, how can they understand your human language? I mean, really, do they really understand human language, or there's something else? Right, people are even talking to LLMs about their emotional side, their mental health. These LLMs are really killing the businesses of the mental therapists. People are really open to talk about their girlfriend boyfriend problems, life problems, financial problems, or any problems in general to LLMs, and they're really fine and they're really comfortable sharing all these details because these LLMs are really good at understanding you and responding you in such a beautiful way that you really feel like I'm talking as if you're talking to a human, right? So what to expect in this video are these questions to be able to understand. So the first question is, what are LLMs? So what exactly are LLMs? I will cover that. How do LLMs work? I'm going to cover high level because there's a video 3 which is based on the transformers that is going to cover the architecture part of the LLMs. But how do LLMs work in this video? What are we going to cover is this thing. Okay, it doesn't understand words. So what does it understand? It understands the semantic of the word, it understands the context of the words. And how does it understand the context of the word, that we are going to see. Okay, so GPT is a generative pre-trained transformer. So we're going to see the architecture of the LLM in the video number 2 after this. But in this video we're going to see it doesn't understand words. So what does it understand? Then what are vectors? Okay, so is this thing related to this thing? Stay tuned for that. What are embeddings? I'm going to explain you what are embeddings, what are the vectors, if they are same, are there any differences between the two. So this question is going to get answered. And then how does AI learn the relationships? So we are going to see the mathematics behind it. How does it understand the relationships between two words, two sentences? How does it understand the semantics? So when someone says, I want you to do whatever you want. So there are two meanings, like literal meaning, I want you to do whatever you want, or the second meaning. So how does an LLM understand the sarcasm or the tone behind it? It all depends on the tone and the voice and how the words are structured in the sentence. But the human can understand that, but how an LLM understand it, we are going to understand the mathematics behind it. So that is going to be craziest thing, like, because I know all of these things. So think of this like, if you watch Demon Slayer, what is that transparency mode, so that they know the internals of it and what is going to come next. So if you know this thing, and I'm going to show you the visual demo. So whenever there's a discussion about the LLMs or the architecture of LLMs, how do they work? Now you have the transparency mode in your mind, like, oh, I know how it works. Oh, I know how it works. Oh yeah, and that's how it works. And this feeling, that's how it works, or I know and I could see through it. This feeling I want to give it to you. And this is why you should come to this channel, because I'm going to make you understand by visualizing it. Okay, so without a further ado, let's get started with what are LLMs exactly. So LLMs are the large language models. So whenever you're asked what are LLMs, don't say like ChatGPT or Gemini or something if you're an engineer. The LLMs, firstly, the long form is large language models. So what are these large language models really mean? So what is the large language models is basically the context size or the number of parameters that a language model has. Okay, and it is so large that those parameters can go in billions, like 7 billion, 10 billion, 4 billion, 5 billion, whatever that number, and preceding with the letter P is the number of parameters that a language model has. And that tells you how large that model is. So fewer parameters equal to it is maybe specialized in one or two things, but the larger parameters means it is generic enough to understand everything. Okay, LLMs are basically a pre-trained models which can predict the next word given the any length of words. So let's say like I say, basically an LLM, you can imagine it as a standard 10th grade student in India who is appearing for the exam. He will like rettamar on all of the, he will like by heart everything, right? Everything, each and everything that there exists in the books of class 10th. So LLMs are pretty much like that, but the exam is not limited to class 10, but it's the universal exam. So LLMs are basically trained on billions and billions of lines of text, even trillions of lines of text, and it has by hearted all of it, like all of it. And that's how it is basically. So whenever, and it has done trillions of times that by hearting process, trillions of times. so that it just knows, like, if you provide any sentence, like let's say I am, and if LLM has the context that like Amir is speaking to it, so he will just say I am Amir. So LLMs are basically, training part of LLM is, it's like, if I had to give the analogy, so it's like, आप जैसे एक छोटा बच्चा आपके घर में है, और उसको अगर आपको बताना है कि ऐसा मत कर वरना पापा, और द नेक्स्ट वर्ड इज मारेंगे या फिर डांटेंगे या फिर समथिंग लाइक दैट, राइट? सो देयर आर लाइक सिमिलर वर्ड्स विच वी कैन फिट इन, पापा डांटेंगे, पापा आएंगे, या फिर पापा मारेंगे, या फिर पापा लेके जाएंगे, समथिंग लाइक दैट, राइट? So LLM does the exact same thing. So if you provide it with the sentence, it predicts the set of words, and depending on the context that it has, it will predict the highest probability word. Let's say papa marenge या फिर papa डांटेंगे. But how does LLM understand this? So LLM understand this using the understanding of the context or the meaning space. Okay. सो छोटा बच्चा बोलता है कि मारेंगे, पापा मारेंगे, फिर पापा डांटेंगे, बट क्यों बोलता है ऐसा? बिकॉज इट अंडर छोटे बच्चे को समझता है, इट हैज द अंडरस्टैंडिंग और इट हैज द कॉन्टेक्स्ट ऑफ व्हाट डजंट इट हैज टू डू, और लाइक दैट बेबी हैज टू डू, so that what are the repercussions of it, if he or she or the kid baby does that thing, what are the repercussions of it, he or she understands that part, things needs to be done, और पापा क्या करेंगे, like the result of the action of his father, what he will do. So all of this context that baby has, that's why he predicts the word as okay, मारेंगे या फिर ले जाएंगे or something like that, right? So LLMs are just the same things. It has trained itself on like trillions of billions of lines of text. It is so well trained that it can just predict if a set number of words is given. So imagine, like, you provide the text only the one word I, then it will predict a set number of words. So let's say, like, if you provide it with the I, okay, okay, so if you provide it with the letter I, and then this is your LLM, right? This is your LLM. Then it will predict maybe I am, or I will, or I shall, okay, and number of words. Okay, so here, from here, what we will do is, there's a temperature parameter. You must have seen this temperature parameter in ChatGPT as well. So it ranges between 0 and 1. Okay, so the higher the temperature, okay, and let's say, like, what LLM does is it predicts the next word. It predicts this next word with the probability, like, let's say, like, this is 99% probable, this is 97% probable, okay, and this is 95% probable. Okay, if we want the definitive or the most obvious options, what we will do is, we will set this temperature value to 0. Okay, and if you want an LLM to be creative, yeah, to explore more options, okay, so what we will do it, we will set this value to higher, which is 1 or maybe 0.7 or something like that. So the higher the value of the temperature over here, the more likely LLM will choose the words from the this bottom part of the list. The lower the value of the temperature, it will choose this part of the words. Okay, so the next one, let's say, like, our temperature value is just 0. Okay, so the next word that is predicted is I am. Okay, so I am. Okay, so now what we will do is, we will pass this next sentence, like, I am, as the input to the model, and what we will do is, we will ask then LLM to predict the next word. Okay, so what we will do is, so it will now return, like, I am Ameer, I am Saurabh, I am Keval, and like a lot of, or maybe I am a chatbot or something like that. Okay, so it will predict that. And now, since the value is 0, it will predict Ameya, but if the value is higher, it might go with the Keval or chatbot. Okay, then this loop continues. Then I am Ameya will get passed, and then the next word would be, and I have a channel called as accidental data engineer, where I, and all of these sentence will get generated. So it goes in this loop again and again and again and again and again and again, and it has done so millions and billions of times for one single sentence, so that it understands what comes next if the list of given words has been fed to it, right? And this is so amazing, like, so after all you can say like gokan patti se bhi sab kuch ho jata hai, and it is like that. But how does it understand कि I के बाद am ही आएगा? But like Amir, you just said like it doesn't understand words, right? So how does it really understands, right? How does it really understand? So how do these LMs really work inside? Backend में क्या होता है? Let me tell you that. But before that, let me give you the visualization as I promised you guys earlier, which is, let me share my screen again. So this is how an LLM will look like. Let's say like our input sentence is the quick brown fox, and if we like, this is the temperature parameter. Okay, so let me adjust to 0 first, or like the minimum first, and I'll just click the generate next word. Okay, so it will adjust it weights, whatever it has to do. This is the neural network that it creates, and then it predicts the word runs, okay, with the probability maybe 30%. It's the highest probability that it has. Okay, so the predicted word is runs, but now the input sentence, if you see, the input sentence is modified to the quick brown fox runs. Okay, but it can jumps as well. It can have that the quick brown fox and the brown leather seat or something like that. That sentence also makes sense. So there is like a lot of text that it is trained on, and but now if I click generate word again, so now it will generate the word and. So the quick brown fox runs and do what, something like that, like do what is, why did I predict it do what? Because I am assuming I have the context that I've read some of the sentences throughout my 28 years of living, that the only sentence makes is okay, the brown fox runs and what does it do, maybe, or something like that. Okay, so I could predict this next question because I had the context, or I had my brain trained like that. So similar way the LLMs do. Let me just adjust this temperature parameter to maybe like close to 1, and let me predict the next word. Okay, so now if you can see, it predicts the runs with the lowest probability. Okay, and let me do it again. Then it is and then let me predict it again. It predicts the, it predict it again, then it predicts sleeps, it predict it again, it predicts and, then it predict it again, it predicts and. Okay, and it does this loop again and 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 again, so that after like billions and trillions of runs over one sentence, and like not one sentence but over the large set of sentences, it understands what exactly the word comes next after a given set of input is fed to it, right? And that's how actually the LLMs are trained. And to train an LLM, it used to take, and I'm not sure like how long it takes now, but it used to take around like 20-25 days to train one single LLM, and it needs a lot of money, a lot of compute, and a lot of power. That's why there are only big players that are coming up with the LLMs, and they are providing their LLM service as a service to others. And there are not a lot of companies that can build LLMs because it requires money, and that's where the problem is. Okay, so let me go back to my iPad. I hope this visualization, I hope this visualization helped you. Like it helped me a lot. Like I would definitely recommend you guys to learn about LSTM. LSTM is long short-term memory. So the short-term memory is for the longer duration. Is the long short-term memory. So learn about LSTM. LSTM is the basic fundamental block of building the LLM. So you can just see like LSTM is a single parametered large language model. But if you take like there are billions and trillions, billions of LSTMs and join them in a neural network and it becomes the large language model. So understand the LSTM first. The LSTM is out of the scope, like this out of the scope of this video, but I would definitely recommend you guys to check out how the LLMs how the LSTM works. Okay, But now, how do LLMs work and what exactly are the tokens? So, in the start of the video, I told you guys LLMs don't, our computer don't understand the words, right? It only understands the numbers, because at the end of the day, everything gets converted into the bytecode, and that bytecode gets converted onto the cycle level, like clock cycle of the CPUs. And machine can only understand that and not the English letter words, right? So, what we need to do is we need to convert everything what we have to numbers, be it videos, images, text, everything. Each and everything has to be converted into the numbers so that the computer can understand it. So, what do you think? Like how LLMs understand Hindi, Marathi at the same time, in English and Spanish and all of these languages? They don't really understand, or they don't really parse, or they don't really pursue these English, like whatever we speak as the words or something. What they do is they convert everything into the common language. Okay, so it is called as multimodality in the world of GenAI, and I will cover the multimodality in the video called as RAGs, and how do RAGs work. But let me tell you guys on high level overview of how multimodality works. Okay, so what we do is we have let's say we have maybe videos. Okay, we have images, we have texts, we have PDFs, and all of these things, right? So what we do is we convert everything into text first. Why? Because text to numbers is easy. Okay, text to numbers is easy, and once everything is converted into numbers, then the LLM can understand anything and everything. Okay, so I will go in more detail about these things in the video number 4, which is the RAGs video. And you definitely need to subscribe to this channel, because I'm gonna make it easier for you to understand everything, right? So what are tokens? What is this line, Amir, have you written here? Like, it's been bothering me since so long that you've talking everything but tokens, right? So tokens are basically words for LLMs. Okay, these are the basic building blocks. Uh, so these are kind of legos of LLM, or words to the LLM. Okay, these are words to the LLM. Okay, what does tokens mean, or how does these tokens get calculated? Okay, so the tokens can be the individual words. Let's say like I am Ameer and I am dancing, and I am dancing. Okay, so the reason why I've used the different shade over here is the tokens can be single word. Okay, so the tokens can be single word, like I am Amir. So the I can be one token, am can be one token, am can be one token. Then this swalpa viram or comma can be one token, and can be one token. But these words like ing, the semi words, are also can be a token to the LLM. It all depends on how the tokenizer model has been structured or programmed. It is just part of the algorithm. Okay, so but for simplicity, we will assume like each word is the token, but it all depends internally how the tokenizer is designed or written. So Amya, okay, now that you've told me what is token, so there is something called as tokenizer. Tokenizer. Okay, and what it does is it gets the input from, so let's say it gets the input as texts or lines. Okay, what it outputs is list of tokens, that this particular sentence has. Or maybe let's say like the sentence is, okay, I know the vectors. Okay, so maybe the output will be I know vector. So this is maybe like the tokenizer. What it does is it gets the input, it turns into the tokens basically. Okay, and the tokenizer output is can be I am vectors, and I know vectors, or dance space ing as well. So anything like that. Okay, now that we have the tokens, or basically the individual words in the sentence, now we need to provide this tokenizer output to something, some black box that will convert these tokens, individual tokens, into a vector space, okay, or vectors. This thing, okay, this particular thing, okay. But what exactly are vectors? And you might think, okay, I thought, come on, I mean, I don't want to learn physics again. And I thought this vectors ended in GE. But no, what are vectors is, these are similar to the vectors in real life. The vectors in physics says the direction and magnitude in the physical world, but the vectors here in LLM tells you the magnitude and direction in the meaning space, the physical space versus the meaning space. Okay, so we have two spaces. So we have two spaces. Okay, now is the physical space, and the second one is the meaning space, semantic space. Okay, so but what are the properties of each of the space, each of the spaces? Okay, so the physical space is the 3D world, or 3D world, three-dimensional. This can be multidimensional, can have up to like 2K to 4K dimensions. Okay, 2K to 4K dimension. So in 3D world, it has three properties: X, Y, and Z. X, Y, and Z. So X axis is the direction in the X direction. Y points denotes you the direction in Y, and the Z points towards like this, like out of the plane, right? So it it looks something like, this. So X, Y, and Z planes, right? But a human mind cannot imagine beyond three dimensions. So I'm not gonna draw it because I don't know how it looks like. But each dimension in the meaning space, let's say like this meaning space, each direction in this meaning space has some meaning to it. Maybe like one direction, one of the dimensions is age. Okay. The other dimension is maybe the gender. The third dimension maybe is locality. I don't know, and no one knows it. The LLM comes up with these dimensions on its own while training while training its own data set, right? But what we do is, if we have to represent a point in physical world, we will represent it as, let's say as this, like 5 comma 3 comma 4, right? So what it means is, go in the five directions to the x-axis, three directions to the y-axis, and four directions to the z-axis, right? In the similar way, also note that the length of this vector, or the length of this vector in the physical space, is three dimensions, because there are three dimensions. Okay, but in the vector space it has like a lot of dimensions, right? Like a lot of dimensions, so the length of is it's fixed. uh, Length of it is fixed, depends on the algorithm that runs behind it to generate the vectors. So I will tell you how these vectors are generated. There are Vectors are basically an abstract concept that AI has learned on its own. That's what I told you, right? It's like the dimension which it has learned on its own. So let's say, like, if I have to represent a vector in three dimensions, I would represent it like this. But there are certain models which are word to vec. So as it suggests is, it takes inputs, turns into the vector. What does a vector mean? Which is, it gives out the certain numbers. Like, let's say I am Ameer is the input. Maybe its output would be maybe 768, 534, blah 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 blah, 1024, something like that, some random numbers. We don't know what this number indicates, but what we know is, if we plot this number in multidimensional space, it will get me some point relative to the origin. That's what we know. Okay, so remember that. Okay, so maybe go something like this, and then go something like this, and go something like this. Okay, so this point represents I am Ameer in multidimensional world. Okay, some coordinates. So this, imagine it as the coordinates of the point. Okay, in multidimensional world, and the number of dimension is a hyperparameter. Okay, I mean, what do you mean by hyperparameter? So for that, you need some understanding of the classical machine learning. So hyperparameter tuning is a whole different story, but hyperparameter is one of the inputs that we can vary while training the model, so that it gives the better responses. Okay, and hyperparameter tuning is a skill that every classical machine learning engineer should have, so that he or she can excel in his job. Okay, but it's a hyperparameter. So a word to vec model has around 768 dimensions already. So whenever we call this word to vec function, or maybe word to vec model, on top of one single sentence, it returns the output in 768 dimensions. So it returns an array of 768 numbers. Okay, so if, let's say, like Ameya is the only word. Let's say Ameya is the only word that we pass to the word to vec. So what it does is the word to vec model. So first the sentence goes to the tokenizer. First sentence goes to tokenizer, and then for every token in the tokenizer, the word to vec model gets called. Okay, so our new pipeline kind of looks something like this now. Okay, so this is input, this is tokenizer, this is word to egg, or any transformer, basically any transformer. Okay, what are the alternatives of word2egg? Word2egg has BERT alternative. The BERT has around, I guess 2k dimensions. So word2egg returns an array of 768 dimensions, but BERT model returns the dimensions in 2000, like 2000 dimensions. So it has more understanding. It really gets into the intricacies of the sentences as well. So higher the dimensions, higher is the understanding of the NLM. Also, with the high dimensions, consider it just as the picture or the video. You can see the video in 720p, a 1080p, or 4K, right? But the higher the resolution of the picture, more the processing power requires for the machine to process that video to render it to you, more the network bandwidth requires. So similarly, higher the dimensions of the LLM, we require more compute to analyze. Also, it can be an overkill as well. So if, let's say, like, I want to send an 4K HD photo to someone, but that someone doesn't care about the quality. What it cares about it, what exactly is the contents of the image. So if I can send that same photo in, like, maybe not in 4K, but in maybe like normal photo without HD or something, and I can just pass the same things, like, let's say I need to send a snap of what I am eating to my friend. For my friend, it doesn't matter if it's in 4K or it's in like non 4K format, right? What it matters to him, maybe like, what am I eating, like pav bhaji or something like that. In the similar way, if your requirement is not that high or not that critical, you can get away with the word to vec model. Which model to choose here to convert your words into the vectors also needs to be decided by this GenAI specialists or the machine learning engineers. So this is something like the system architect level problem for the ML engineer. Okay, but anyways, so now the word to vec, what it does is, the tokenizer gives you the list of words. The word to vec will give the numbered output for each of the words. Okay, each of the words. So it will give you the array of words. You understand, right? For every words, the array is returned. So it has like structure like this. Okay, each word, like, this is I has 768 dimensions. So I am has 768 dimensions. Amir has 768 dimensions, something like that. And each dimension the higher the number on that particular axis, the more the LLM understands about that dimension or about that word. Okay, so each dimension has the meaning. So we are plotting our vectors or our each and every word in the meaning space. Okay, in the meaning space. Okay, so now let me give you the understanding of the embeddings. Okay, now we are really getting into it. Okay, so what exactly are embeddings? Okay, so whatever the output is returned by the BERT model or the word to vec model, it returns a vector, right? 768, 128, maybe 7, blah 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 blah, and then maybe 762 or something like that. So if and only if, so we call this array, a one dimensional array, as a vector. But let's assume like each of these numbers has some meanings, right? Each of these numbers has some meaning around it, because this 768 is not just a random ass number. It really represents some value along that particular dimension, along that particular meaning. Maybe it denotes the gender male, the 768 in that particular dimension space, right? So, and this 128 maybe represents like he is 5 feet 6 or 5 feet 8 or something like that, right? These numbers has a meaning in the meaning space of the LLM. So when a vector or the numbers inside the vector has meanings, we call it as embedding. So the embedding is a special type of vector in which the numbers has meaning. So we call it as embeddings. Okay. So every word has its own embedding, and that embedding we store it in the database. So what we do is, now I am Ameer has like each one of these vectors, each one of these words has their own vector. So what we do is we store in the vector database as I represents this array, am represents this array, like something like that, something of this sort. Okay, so that an LLM would know how to map between these things. I'm not sure if it really stores it like this. I'm just giving you the visualization part or giving you the idea how it stores in the store. So since we are storing the arrays or the number of arrays in the database, so there's a special type of database which is the vector database, which is just meant to store these types of data structures, which is optimized for these types of data structures. And that's why we use the vector dbs, or there's a new database term which is vector dbs. We're gonna go through that, what are vector dbs and everything, in video number 4. But this is to give you ideas. These are vectors, and we store these vectors in the database, and we retrieve those vectors fastly. So the traditional databases are not meant for these concepts, because these concepts are new, right? The databases are also evolving. So the vector data, this is the vector database basically. Okay, so the embeddings is a special type of vector which has meaning in it. Okay, but Ameya, how does AI understand the relationship between these words, or how does it understand the semantic behind it? In the start of the video, you told me it understands the taunts or sarcasm and everything, right? So how does it understand the semantic meaning of the sentence, or what am I trying to do, or what I'm trying to say? How does an LLM understand these things, right? So for that, let me let me walk you through this section of the video, which is how does AI learn these relationships. AI is not the only one who needs to know what a relationship is, right? There's a very famous saying, or the very linguistic principle is, you shall know the word by the company it keeps. Okay, so it follows this principle to know the semantic meaning. So what do I mean by that? What do I mean by this? So you shall know the word by the company it keeps. So you've often heard from your parents like you are the average of the 5 people you hang out with, right? So LLM understand these relationships is when it has plotted all of these vectors into its vector space, right? So let me just draw it for you. Let me just make it more easy for you. So let's say like this is the dimension x, maybe this is one more dimension, this is one more dimension. So this is the age dimension, this is maybe the concept dimension, and this is maybe the gender dimension. Okay, and there are like many more dimensions, like multi-dimensional mode. Okay, so now let's say like I am a mayor. Okay, I am a mayor is the word. So maybe I am a mayor gets plotted over here, somewhere here. Okay, so it has somewhere here like I. So the am may be something somewhere over here, am, and then a mayor may be here. Okay, and let's say like the next sentence is I am Anushka, I am Virat, I am Ninad. Okay, so now the LLM has the coordinates of I are same, but so now so I gets plotted here, am gets plotted here. Okay, the only difference is am, Anushka, Virat, and Ninad, right? So what LLM will understand over the period of time, over the period of training of it, is I can plot all of these names here. Here, okay, so it can plot Anushka, or maybe first Virat here and then Ninad here. Okay, and it might plot, so these are the vectors pointing to I am Ninad Virat. Okay, and this can plot the Anushka somewhere down here. Okay, somewhere down here, Anushka. Okay, but now next time let's say I am Vaishnavi comes. So the LLM knows, okay, Vaishnavi is like her gender is something different than Ameya Virat and this thing. So it will know like Vaishnavi should go over here. Vaishnavi should go over here. Similarly, when it comes to the words like fruit, apple, red, mango, all of these things, right? So it will plot somewhere here, like all of the mangoes, pineapples, and everything will go here. Maybe the red will go over here or something like that, because it will be closer. So the apple will be here, so it will be closer to the apple because red is related to apple. And maybe yellow would go here, because mangoes are here, because mangoes and oranges are here. Okay, so when an LLM gets trained on millions and billions of lines and millions and trillions of words, so it plots this spear inside of it, right? Now it knows I am के बाद विराट या फिर अनुष्का या फिर something आता है, and I know I have observed all of these 1,000 names already. So if the 1,000th one, like, for the new word comes in after I am, so it will know like to look in this direction. So I am Ameya. So the next word, let's say Viraj is there. So Viraj, I need to plot it over here, somewhere here, right? So it knows. Okay, so if I'm looking into the apples and everything, so from here I would look in this direction. Okay, I need an apple. So an LLM would know, okay, I is somewhere here, apple is somewhere here. So I need an apple juice maybe somewhere here. Okay, so I need an apple juice. Okay, so it will plot it somewhere here. But how does it goes to here? So how does it know the next word should, it will look juice over here? How does it know? Okay, so let me explain you how does it know. Okay, let me insert a slide here. Okay, how does it know the relationship? So let me give you the mathematical representation of it. How does it know? Okay, so what it does is it first converts the, so remember our diagram over here, right? So first the tokenizer comes, then word to vec, then comes sentence vector creation, and it has the semantic meaning. This step has the semantic meaning. What do I mean by that? Okay, so let's say I am a mayor and I need an apple juice. That's the sentence, or maybe the sentence is I am a mayor and I need an apple, and there is apple, and I'm just asking to predict the next word to LLM. Okay, so remember this thing, the very first this thing, I am, and then goes to here, then goes to here, goes to here. So similar thing, I'm asking it here. I'm asking it here. Okay. So how does it know to what to predict is, so first it will go and see, okay, I need to see in this direction, okay, I, and then where is am is downward. So what I'll do is I'll go in this direction first in the vector, then I'll go in this direction first, I am, then I will go in this direction first, then I am a mayor. Okay, and then wapas I'll go in this direction, I, then maybe somewhere need is here. Okay, so need is here, I need, then I'll go in apple direction, apple direction, am an apple, and then, so how does it know to go in this direction, go in this direction? So if you know from physics, if you add all of these vectors, right? So let's say, like, what you do in physics is, let's say the vector a is here and vector b is pointing like this. So what does it mean is, you are going in the direction of vector a over here with this magnitude, and then you are going in the direction of vector b from here. Okay, vector b. So what is vector a plus vector b is, as if you've gone from this to this point, correct? As if you've gone from this origin to this point, which is vector a plus vector b, correct? So in the similar thing, and if you are not clear about this, go to Byju's or YouTube or something like that and understand how vectors work in the physics from 11, 12, 13, 11, 12 standard. You will get to know it. These are just the basics of it. Okay. So what LLM does is, it adds all of this direction and all of this direction, and once you add all of this direction, and it will definitely will point to this direction for sure, for sure. That's how the vector addition simply works. That's how the vector addition simply works. Okay, so in this direction, when I will see in this direction, I will see, like, oh, there is a juice, there is a salad, there is maybe, what is apple pie is there. Okay, so there is a salad, there is apple pie is there. Okay, so this thing and this thing. So I know my answer lies somewhere over here in this space my answer lies, right? So what LLM does is, it predicts, okay, 90% I'm sure it's apple juice, maybe 80% I'm sure it is an apple salad, and maybe 70%, if you guess, so I need apple pie. Okay, so remember from the visualization that I showed you earlier, where it predicts the numbers. So where it predicts the number over here, let me just, so where it predicts all of these numbers. So where do these numbers come from? So it comes from this direction. It comes from the direction of this. Okay, and how do you calculate, like, what are the number of options that you would want? It calculates using something called as similarity score. Straightforward answer to this is, what is similarity score and how does it calculate is, let me take you back to the physics vectors again, which is a and b. So you would want to know how close are these vectors, right? Or how close are these vectors? And by now, at least we have an understanding is, the vectors which are similar to each other lie very close to each other. This is the angle theta between the two vectors. Okay. So now I want to know how these two vectors are similar to each other. Okay. How these vectors are similar to each other. So you might know there's a function. Okay, to know this, what we do is, we project this vector on top of this, or we can project this vector on top of this as well. This is the right angle triangle. So for the simplicity, we would project this vector. So if we project this vector on this one, so it will look something like this. Okay, something like this. So this is the 90 degrees angle, and this is 90 minus theta. Okay, and we know, like, the cos theta is, cos theta is adjacent by the hypotenuse. Theta is 0, the cos of 0 is equal to 1. Okay, so if we want, like, two vectors to be similar, or to have the meaning or the semantic behind their vectors to be the same, we would keep these vectors as close as possible, and if we want, like, these vectors to have, like, different meanings, then they would have the different angles to them. Okay, so if two vectors have the small angle, small theta between them, these are very similar vectors. Okay, and if we want, if two vectors are literally in opposite directions, their angle is 180, it's minus 1, right? And cos of 90 is literally 0, 0, right? Cos of 90 is 0. So if the more the angle, the more is the dissimilarity between them. The closer they are the more similar vectors are. So the same concept applies here as well, because at the end of the day, it is just a vector in multidimensional instead of one single dimension, right? So how do we calculate is using cos theta. So magnitude of A into magnitude of B into cos of theta is the formula to calculate the similarity score. And what this similarity score, since we are calculating similarity using cos, so we call it as cosine similarity. Cosine similarity. So the cosine similarity lies between 0 and 1. Since it lies between 0 and 1, the product of A into B gets multiplied between the range 0 and 1. So the entire product or the entire thing lies between the range of 0 and 1. So the more the number, the more the cosine similarity close to 1, the more is the probability of getting this vector similar. Okay. So if we map all of our sentence in the space, so our sentence semantic would point at this. So I am Ameer and I need apple. That vector will point to this. Okay. And how that vector gets plotted? How that vector gets plotted is, it is nothing but it is the sum of all of the points. It has array coordinates as 7, 8, 9. Okay. Am has 100, 150, 250. Again, Ameer has 0, 0, 500. Okay. But I here, I'm here, I'm here. So if we go, so remember from this diagram, right? What is the addition of A plus B? Why do we want to calculate A plus vector B, or vector I plus vector am plus vector Ameya is? Because we would want to know where the next word will lie, right? If we go in the direction of I and then go in direction of M and then go into direction of Ameya, then wherever that vector points, we would know the next word would come from that particular direction. So here, let's say like I go in the direction of I, then I'm going to the direction of M, and then I go into the direction of Ameya. So like I am Ameya. Okay. So the next word would lie somewhere in this space, somewhere in this angle, somewhere in this angle, right? So we are eliminating the everything and we are just looking into this angle. Okay. So let's say like I am Amaya is right here. So what we know from our diagram or the vector diagram is, it is as good as seeing it from origin and going to this point, right? Going to this point. Okay. So now we know like our answer lies somewhere here. So what we would do is this. Let's say this is our sentence vector. This is our sentence vector. Okay. Now what we do is we will calculate all of the vectors around it using cosine similarity, and whichever vector is closest to it, we will just return that particular word as output, the next word as output. So the same concept, if I had to give you, so how we will calculate the sentence vector is, it is the sum of these coordinates. So let's say 107 divided by 3, the number of tokens in it. Then let's say 158 divided by 3, comma, 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 and then 500 plus 250 plus 9 divided by 3. Okay. So then we will know the coordinates of the new vector, and that would be our sentence vector. Okay. That would be our sentence vector. Okay. Okay. So the step 3 is done. Okay, so the first tokenizer comes in, then word to vec comes in. Like a word to vec has the alternatives called as BERT and all of the other models as well. Then comes in the sentence vector. So each word once calculated, then it gets converted into the vectors of every word, and the vectors of every word, if it's a sentence, gets the sentence vector gets created. And from the sentence vector, there comes in the block which is similarity score. So then according to the similarity, it will predict the next word. So it gives the output, the list of words. Okay. And now that it has the understanding of list of words, it will just, depending on the temperature parameter, it will predict the next word. And it will again sentence vector next word, sentence vector next word, sentence vector next word, sentence vector next word. It goes into this loop and it gets the entire sentence until you say stop, or something like that. Otherwise, it just keeps training itself, keeps training itself, keeps training itself until it finds, until it completes its training, right? Okay, so now that we have understood like how this similarity works, so let me just recap everything. What we done is we understood what are LLMs, we understood how do they work. If it doesn't understand words, what do they understand are the numbers, tokens, and the vectors and the embeddings. I gave you like what are vectors, I gave you what are embeddings. I also gave you the understanding of how does an AI understands these relationships. I give you the mathematics behind it. Also, this was very high level overview of LLM. Okay, if you want to go in detail, read the research paper, read the detailed books, read the detailed blogs about it. I try to list down all of those into the LLM. This was to give you high level understanding of how do these things work, how does this cosine similarity and everything comes into the picture, so that it can understand the semantic behind it. How does LLM stores our English data or Marathi data, whatever the text data it is, into the numbers in their vector DBs or so, and how does it find out the similarity and everything. So if you have understood this part, you will definitely understand the part where the RAG comes in. Okay, but that you have to wait for the video number 4, because that's gonna be the most interesting video of all time, because the building an LLM is not a thing anymore. The LLMs are built. The new thing in data engineering, or new thing in this AI world in general, is the building RAGs, building your own knowledge bases and everything, and that I'll talk about it in the next video. But stay tuned for that, and make sure you subscribe to the channel. Only the last part of the video is remaining, which is the demo and the demo time, and I'm so pumped to show you all of these things in the visual format. But before that, I'd like to request you, if you haven't subscribed to this channel, hit the subscribe button, hit that like button, because it really motivates me a lot to make these videos again, because I work full time, as you know. So managing everything and making these videos is like very hard time. Today, like right now, the time is 2 a.m. in the morning, or like 1 a.m. in the morning. So I'm still making these videos at night, so that I can give you like a lot of content for you to digest, for you to understand, and I try to make it easier for you. If you understood it so far, just give me a thumbs up. Write me a good video in the comments, or like motivate me in the comments, pump me in the comments to make these videos more and more and more. And don't forget to follow me on Instagram at accidental data engineer, and follow me on LinkedIn at Ameer Bhilegaonkar. And let me show you the demo, and which is the most exciting part of this video, and I'm so pumped on this. Let me reset this. So now we have understood, like, given a sentence, how does it predict the next word, how does it come up with the next word and everything, right? This lazy and everything depending on the temperature. But now let me give you the visualization of this thing. So let's say I give you the sentence, happy dog ran in the green park. And if I click visualize, okay, so let's say the first gets this thing, okay, first gets the coordinate this thing, dog gets the coordinate this thing, ran gets the coordinate of this thing, and it gets plotted in this semantic space like this, right? Every word gets plotted in the semantics like this. Par gets this thing, okay, and everything. Now the next step is to create a sentence vector out of it. Okay, for some reason this didn't work for me, but we will just imagine like this vector points in, so the green arrow, okay, so the green arrow points in this direction somewhere, so this direction somewhere. And we know like the sentence vector points lies somewhere here in the space, maybe somewhere here in the space. Okay, let's just assume that. And now we will ask it to predict the next word. Okay, so now it will come up with these sentences, these three words. So I've coded to give it top three words, so which are and, was, and at. And the similarity score to it was maybe 98, 95, and 96. Okay, depending on the temperature, it will just choose the next word. it will go again in the loop, and let's say the next word is and. uh, the next word was and then if we click visualize again, it will just do the entire thing again, and it will come up with this part. It will visualize it like this, and it will again create the sentence vector with the new sentence plus the word and as the input. As I told you, park, then buy, and now the word and gets plotted. And now if we create the sentence vector, the sentence vector might plot in some other direction. Okay, right now it just gets you the same direction, but let's say like we have different direction. And now if we click predict the next word, it will again come up with is, or for, these three words it came up with. And then it comes up with the similarity score. Whatever the top similarity is, it will just predict that, and then again goes into this loop. And this process happens like very fast. Okay, this simulation is very slow, and is to make is to make you understand like how it works. Okay, how it works. That's why it is slow. So imagine this process is happening millions of time in 1 or 2 seconds. So imagine like how fast it is learning about everything to predict the next word, right? So that's how it predicts the next word. Okay, and now let me give you another simulation wherein everything is plotted in the 3D world, which is the semantic world, or the meaning space. So the x-axis represents the concept, the y-axis represents the gender, and the blue axis represents the age. Let's say like we are maybe doing like man runs faster than women or something, or maybe let's see instead of this, maybe maybe queen eats the red apple. Okay, let me plot it. Okay, so now these three vectors gets plotted, and now the sentence vector gets created like this. Okay, so it is an average of these words, and the sentence vector is like this. So the next word is probably in this direction somewhere, right? That's what I was telling you. Okay, so let's say like so if you can see on the right hand side, the sentence vector is getting created. Sentence vector got created, and it has the coordinates of these things, which is the average of all of these things, right? And now if you see the dynamically generated vectors, the cues for these new words, the new words are basically it's green apple and all of these things, the red or something like that, right? But now let's say like the LLM has learned to plot all of these things, right? But let's say how this sphere will look like is, let me give you this analogy of countries versus royalty, right? Let's say our sentence is the king of France and the queen of Italy. Okay, so now what we know is, so Italy and France gets plotted like this, but the king and queen gets plotted like this. Okay, if there are any royalty related things, we should be looking at this particular vector or this particular line or this particular angle. So we would know that all of the royalty related things like king, queen, senapati, or maybe cavalry or something like that lies in somewhere in this particular direction. But if we look at this direction, let's say where the Italy, France, and everything is, if we look at this direction, we would know maybe India will lie somewhere here, US maybe lie somewhere here, or China may lie somewhere here or something, right? We don't know, but we know for sure that if we look in this direction or something like that, this particular dimension has all of the countries. This particular dimension has all of the royalty things, right? So there comes the multidimensional property of it. Since we cannot imagine more than three dimensions, I'm just give you the imagination that if there was one more axis going through this and the queen, that would be the royalty axis. If there is a dimension or the axis going through these 2 points, it would be the countries or the places or the geography axis, right? If we plot like fruits, right? If we plot like fruits, then all of the fruit related words would lie on this particular axis or this particular dimension from here to here, right? So like once all of these sentences it has, so the core vocabulary, this model particularly is trained on only on these particular words for simplicity. But let's imagine the core vocabulary of an LLM has trillions of relationships. Trillions, not billions, not millions, trillions with T. It has trillions of relationships. Once this plots all of the spheres, and it is very, very complex and very, very high dimensional. Can you imagine 768 dimensions? Only in three dimensions with all of these words, it is hard for me to gather or understand things, right? And it is just the visualization. It is just the visualization. Okay, LLM does not really plot all of these things in his mind or something like that, right? It just the vectors get stored as numbers into the vector db, and it is represented in some multidimensional world out there like this. The visualization is just for you to understand. Okay, the visualization is just for you guys to understand. So just imagine there are 768 dimensions, 762 dimensions, which is word to vec model. If you go to the BERT model, there are like 2000 dimensions, and if the higher and higher dimensions, it gets more and more tricky and hard for the companies to train the higher dimension models, because one single word has 2000 dimensions, and one single sentence has those many tokens multiplied by those many number of dimensions. And if we have the billions of texts, right? So it has billions of texts multiplied by billions and billions of the tokens multiplied by the number of dimensions that it has. So it is very, very, very important for the ML engineer or a GenAI engineer to tune the hyperparameter of the dimensionality very well, so that trade-off between the cost compute versus the quality of the output. That was it from my side. I hope you understood all of these things. I like creating these demos. It took me like quite a lot of time. Also, I have developed these demos using GenAI, of course, but coding these, coming up with what I am imagining to the actual code and vibe coding with the Gemini and everything took a lot of time, and it takes like a lot of time to make these videos. It would motivate me a lot if you just like this video, subscribe to this channel, and leave a sweet comment for me, so to motivate me, pump me to make more and more of these videos, because my target is to at least complete these 7 8 videos of the series. And so when I come back from India, I will make more advanced level of the video. So now that you have the understanding, the theory part of all of the LLMs after this entire series, I will go ahead and make the videos on the projects, creating MCP servers, creating the entire agentic pipeline using all of the agents and everything. So by that time, you would have understood the theory of it. And now practically we will go ahead and go gets our hand dirty in the field of Gen AI, agentic AI, all of these fancy words out there, right? So I hope you understand everything, and I hope you have that transparency mode vision now. So that anyone asks you what is an LLM, you don't just say it's a ChatGPT. And that's it from me. I hope you like this video. I hope you enjoy it. With this note, हंसते रहिए, हंसाते रहिए और खुश रहिए, and I will see you in the next one. I'm grateful, oh yeah, ain't